Hi everyone, welcome back to A207 Data Communications and Networking. We are now at Chapter 7, and in this chapter, we discuss resource allocation in networking, as well as some of the problems faced. My name is Nuruddin, and with me is our A207 student, Matthew Tan.
Hey everyone.
In Chapter 6, we discussed how protocols work to establish, maintain, and ensure reliable communications between online entities. In this chapter, we need to understand that a network is a finite resource in itself, and that various management techniques are needed to facilitate smooth communications. To begin with, we need to understand that resources in networking are both fixed as well as limited. A network's speed is made up of two components, throughput and bandwidth. Now Matthew, what are throughput and bandwidth again?
Throughput is something like the speed of water in a stream, and bandwidth is how wide and deep a channel really is.
That's an excellent parallel, Matthew. This also makes it very easy to visualize. Next, just like a real stream, speed, bandwidth, and throughput can be upgraded, but only after physical changes to the stream itself, or the network hardware, and certainly also the configuration settings behind them. So if we do not consider upgrades, resource management is now the key issue here. When too much data is sent to or from any network node, the end result will be a queue which can get congested and suffer from overflowing. Overflowing causes data to be lost due to packets being dropped through timeout, and in turn leads to network congestion.
So, do we need to deal with controlling resources or controlling congestion?
Why, both of course. Effective management will actively allocate network resources, reducing congestion to a barely perceptible minimum. We come to the concept of using a queue to manage traffic through a router. In addition to routing mechanisms, the queue is actually a small amount of high-speed memory, RAM, where data packets wait before being routed. The diagram here illustrates how a queue works. Just the same as in a real queue, data passes through the memory buffer in a first-in, first-out system, FIFO. Priority queuing is similar to a VIP queue in real life. VIPs will get ushered into a fast-track exclusive queue, but if there are too many VIPs, they too will end up having to wait their turn. Fair queuing, on the other hand, assigns data from each source to its own queue, which creates a fairer system than regular VIP queues by themselves. This diagram shows the concept of a fair queue. Each flow represents the sum of data from a single source. However, fair queuing may end up being unfair on high-traffic nodes, as they will have a queue that is continuously packed. This formula shows how data gets queued in a fair queue. Continuing with that formula, this shows how the maximum time that a packet finishes being transmitted depends on packet's length, its start of transmission time, and its arrival time. That gives rise to the concept of timestamping. Each data packet will have a unique timestamp, as no two packets are sent at exactly the same time. Now let's take a look at fair queuing in action with some numbers. In the same length of time, smaller sized packets will be cleared faster, as a large packet will take a longer time to process. TCP uses different policies to handle congestion in the network. We describe some of the policies in this section. There is the slow starts method, shown here. What happens is, resources are slowly added, but only after congestion starts to happen. There is also the method of congestion avoidance, shown here. What happens is, resources are proactively added such that if congestion starts to happen, resources can continue being added such that it's not a problem anymore. In TCP repeatedly increases the load it imposes on the network in an effort to find the point at which congestion occurs, and then it backs off from this point. Quality of service, or QoS, is a concept introduced to ensure smooth delivery for different data types. As network usage evolved, data such as voice, video, and multimedia have grown to demand more network resources. QoS acknowledges these more demanding applications and moves to categorize data flows and best cater to them. Even transferring regular data and text files will consume resources if the files come in large sizes and numbers. To summarize, The distinguishing characteristic of real-time applications is that they need some sort of reassurance from the network that data is likely to arrive on time. This implies that the network will treat some packets differently from others, something that is not done in the best efforts model. A network that supports these different levels of service is said to be a QoS-enabled network. That sums up our discussion on resource allocation and management. Remember to post any questions onto Google Classroom. Work hard, work smart, work your way to your dreams.